So we talked about reacting mixtures, and we talked about the stoichiometric coefficients in a reaction equation and how it's balanced. Now we need to move into doing an energy balance for reacting mixtures, and then there's some new things that we have to cover. So when you have a system, fuel coming in and some source of oxygen, either it's O2 pure or it's O2 plus 3.76 N2, you have to have some source of oxygen. Reactions are more general than this, but we're focusing on combustion. What goes out are products. Products like CO2, carbon dioxide, H2O, water, and you could have some unused or uncombusted oxygen, and you could have the nitrogen if you typically had nitrogen coming from the air. Is on the left-hand side, we have all the reactants. Right-hand side, we have the products. Now, if I did an energy balance for a control volume where the reaction is occurring inside the control volume, we could have a heat transfer, a rate of heat transfer into the control volume, staying with our traditional thermodynamic sign convention, and a rate of work transfer or power out of the control volume. We'll add a little subscript CV and a subscript CV indicating heat transfer into the control volume and work transfer out of the control volume. Both of those are rates. So if we write the first law analysis, there's a couple ways of writing it. Just do all the ins, the rates that are coming in are equal to the outs. We have Q dot in. We also have the mass flow rate times the enthalpy summed over all of the reactants coming in, equal to the out. Shaft power out of the control volume plus the sum M dot H's for all of the products. Think for a minute. Should we work on a mass basis or on a molar basis? We just finished balancing reaction equations, right? What does those stoichiometric coefficients in front of a balanced equation represent? The amount in mass or the amount in moles? Moles. So we really want to move and think now in a molar basis. So this is more of the way you write it. The rate of heat transfer in minus the rate of shaft work out is equal to the sum of the molar flow rates of every one of those products times its molar enthalpy summed over all of those products which are exiting. I know I'm trying to use the notation in the textbook. They use P underneath the summation sign, and then they'll use E for that are exiting, minus the sum of the molar flow rate times H bar of all the reactants that are incoming. Okay, give me the units on N dot. Kilomoles per second. Give me the units on H bar. Kilojoules per kilomole. Now we're a little bit of a quagmire, because let's take a real system. Let's think about an example. Something that is not too complex, maybe one of the simplest combustions that we could study. Let's see, we introduced a bunch of fuels last time. Methane, octane, methyl alcohol, propane. Those are going to be pretty complex. But then we had just H2 by itself, hydrogen by itself. That's pretty simple. Or even carbon by itself. Of all of those that I mentioned, do you think carbon by itself might be one of the simplest to study as an example? So let's do that. So our fuel is just going to be carbon. And just say it's solid. In a typical system, you pulverize it, get it to very fine powder, throw it into the combustion chamber, okay? And I know that often we get the oxygen from air, but if I include air, I have to track along with the nitrogen. I think it's simpler. I know it's less realistic to get pure oxygen. But let's just say we have pure oxygen gas coming in. So I only have two reactants. What is the product going to come out? Am I going to get any water vapor? Am I going to get any? So no. Let's do this. Let's say it's 100% theoretical oxygen. So there's no unused oxygen coming out. Just the perfect amount. Let's write our balance equation for that. So we'll have carbon, leave a 1 in front of it for the stoichiometric coefficient because it's our fuel. Leave a space for how much oxygen we need. Come over here, carbon dioxide. Let's balance the carbon first. What's in front of the CO2? Good. And then come back and balance the oxygen. What's in front of the O2? Did I balance that right? This is really the simplest reaction equation we could do, right? Pretty simple coefficients, almost too simple sometimes. But now we want to write out this energy balance. So we have, for this system, maybe I should write it right here. We have Q dot, and I'm going to have of the CV minus W dot CV is equal to the sum over the products. How many products do I have? Just one. So it's going to be the molar flow rate times the enthalpy on a molar basis of the carbon dioxide minus the molar flow rate times the enthalpy on a molar basis for the carbon minus the molar flow rate, the enthalpy times for the oxygen, right? We know how to do differences either on a mass basis or a mole basis for the change in enthalpy of water or ammonia or refrigerant. But how do I compare the differences between carbon, carbon dioxide, and oxygen? Well, I'm glad you asked, and I'm glad other people have studied it before us. Because what they'd said was, we could go back and look at base elements, the most fundamental or foundational way that matter occurs in our world. And from there we can model how it could build up or make a more complex molecule like methane, or make a more complex molecule like even carbon dioxide is viewed as more complex than the basics. And so some of the most basic are oxygen diatomic, hydrogen diatomic, nitrogen diatomic, and carbon solid. To be able to relate them all on the same basis, you introduce the enthalpy of formation at standard conditions. So here's a new symbol, and it's called the enthalpy of formation. And each element has a value for its enthalpy of formation. Some of them, if they're a base element, its value is 0. Others, it's non-zero. Most of elements, it's non-zero. Only the most basic are. So what does this measure? It measures the energy or the enthalpy associated with the chemical composition of that element compared to reference state of base elements. Okay? So it considers how that element may have been formed, enthalpy of formation, from more basic elements. So if I want to know H, it's the sum of the enthalpy of formation plus the enthalpy at the current condition. This is the carbon dioxide. It's a product. It's going out. It's exiting at the exit temperature minus the enthalpy at the reference condition, the reference temperature. The reference temperature is 25 degrees C or 298 Kelvin. That's how you expand this one term. Each of those enthalpies on a molar basis is a combination of the enthalpy of formation and then the difference between the current condition and the reference state condition, 298 Kelvin, 1 ATM. So let's expand out the equation. Q dot and minus W dot is equal to the molar flow rate of the carbon dioxide times enthalpy of formation of the carbon dioxide plus the enthalpy of the carbon dioxide that's exiting at that exit temperature. It's a function of its exit temperature minus the enthalpy at that reference. I'm just going to put 298. Okay. Then you have minus the molar flow rate. There's a dot on these ends of the carbon, the enthalpy of formation of the carbon, plus the enthalpy of the inlet temperature, the carbon at the inlet temperature minus enthalpy of 298. Then you have minus n dot of the oxygen, enthalpy of formation of the oxygen plus the enthalpy as a function of the inlet temperature of the oxygen minus the molar enthalpy at the reference temperature of the oxygen. Make sense? A lot of times these terms are just expressed as a delta H bar. Compared to the reference temperature, what is the enthalpy? All right. Well, how do we find the enthalpy of formation for each element? We go to a table. And so table A25, look at the title for table A25. Thermochemical properties of selected substances at what temperature and at what pressure? So that's the standard temperature and pressure. So let's take a look at the first column. It's our substances listed down. Now I truncated it and threw in methane, and then I threw in methanol. So this has been truncated, deleted a number of entries. The formula for carbon, C with a parenthesis S. What does that S indicate? Solid. What does the parenthesis G on this H2 mean? Gaseous. What does this L on this H2O mean? And what does this G on this H2O mean? So right away, you better watch out. Water could be in the liquid state at 25 degrees C, or it could be in the vapor state at 25 degrees C. True? It can. It can go out. Water vapor can go out in a product stream, and as long as its dew point temperature, or the temperature of the product stream, is above the dew point temperature for that mixture, it's not going to condense. It'll go out in vapor. It doesn't say that the partial pressure of the vapor is 1 atm. It didn't say that, because typically it's in a gas mixture all at 1 atm. Okay. Notice also for methanol, look at the G and look at the L. What does that mean? Methanol at 25 degrees C could be liquid or it could be vapor. Okay? Methanol is like a fuel. That's what it is. Okay. Now let's move over to this column. What is there? Molar mass. Big M, units kilogram per kilomole. Some of this information is repeated in other tables, but some of it's unique. Okay? Here is the new column. Enthalpy of formation at that standard condition. That's what that superscript naught means. 298, 1 atm. Units of kilojoules per kilomole. Notice some have 0 values for the enthalpy of formation. Carbon, hydrogen, diatomic hydrogen, nitrogen, diatomic nitrogen, oxygen, diatomic oxygen. They have a 0. Why? Because they're like the most basic, and they're happy at that state out in the atmosphere. And then the other ones have non-zero values for the enthalpy of formation. Where did these values come from? Some tedious experiments. Thankfully, other people did it and report their data, and we can use it with confidence. Because carbon dioxide, no matter where you're at or when, it all behaves the same. Now, what about the next column? Gibbs function, we'll get to that later, not today. Absolute entropy, get to that later, not today. And heating values, hopefully we'll get to today. Heating values. All right? So what you could do is you can write a general equation for combustion or reacting systems. Here, if there's any heat transfer into the control volume, any shaft work out of the control volume, the flow of the products. And notice what they did was they took the whole thing and divided the whole equation, which I had before, by N dot of the fuel. That's the molar flow rate of the fuel. If they do that, then you're going to have a ratio like the molar flow rate of oxygen divided by the molar flow rate of the fuel, which is equal to the stoichiometric coefficient of the oxygen. And so this N without a dot on it is the stoichiometric coefficient in our balanced reaction equation. Okay. One of those N's for a reactant coming in is going to be 1. That's the coefficient for the fuel, because N dot of the fuel divided by N dot of the fuel is equal to N of the fuel, which is 1. True? It's kind of trivial, but. And then we have the enthalpy of formation for each of those entities. Some of those are 0 values for the enthalpy of formation. And what's this delta H bar? This is for the products. If it goes out hot, that delta H bar is non-zero. If it goes out equal to 25 degrees C, if the products go out at the standard temperature of 298 Kelvin or 25 degrees C, is this equal to 0, this delta H bar? It is. It is. Now, often our products go out warm after combustion, but a lot of times our reactants come in at standard 25 degrees C. So a lot of times this term is 0. So it may be a little overwhelming, but some of these groups of terms are 0 in our equation. But what equation is this? This whole equation? Energy balance. First law of thermodynamics. It's for reacting systems. When you have reacting systems, you have to have the enthalpy of formation, so you have a common datum point for all energy or enthalpy measurements. Ready to solve a problem? Let's go back to the same simple problem of combustion of solid carbon. So we have a reactor, we have carbon in the solid. We're going to come out with the CO2, and we're going to use pure oxygen. This is now burning with 100% theoretical air, isn't it? So guess what? It's going to begin like this. So let's write our balanced reaction equation. It looks like this. C plus O2 plus 3.76 N2 goes to CO2, it's a 1 in front of it, plus, and then there's a 1 there, 3.76 N2. Did I do that right? 100% theoretical error. Okay. And the airstream comes in. This all on the temperature in is 25 degrees C. The products exit as gases all at an exit temperature of 25 degrees C. So it goes out N2, 3.76 N2, right? So, neglecting changes in kinetic and potential energy effects, determine the heat transfer to the furnace from the surroundings in units of kilojoules per kilomole of the fuel. They want you to calculate Q dot in the CV divided by N dot of the fuel. Where's my control volume? Right there. True? All right. So this is a furnace. Is there any W dot out of the CV for a furnace? No. You just have to know that there's no power going out. All right. There is, we're going to put this as Q dot CV is positive going in, and we know that the answer we're going to calculate is going to be a negative, and here actually is the answer that we're going to calculate. Okay? Make sense? So let's go ahead and write our energy balance equation and then cancel the terms that are 0. So we got W dot CV over N dot fuel. Right? And now what do we have? We're going to have the products. Let's do the stoichiometric coefficient times the enthalpy of formation plus the change in the enthalpy, all of that for the carbon dioxide, plus the stoichiometric coefficient enthalpy formation plus the change in the enthalpy if it's hot or cold for the nitrogen, minus the stoichiometric coefficient times the enthalpy formation plus the change in enthalpy if it comes in hot or cold for the carbon solid, plus or minus these. I'm going to run out of room, so let me move over here. Minus the enthalpy formation plus delta H bar, all of that for the oxygen coming in. minus stoichiometric coefficient, enthalpy formation, nitrogen. All right, I pause. Do you like that equation? Let's point out some things. It looks like this is nitrogen and that's nitrogen. What? One place I'm adding nitrogen and one place I'm subtracting nitrogen. It can be very confusing. But this is the nitrogen that's going out with the products. This is the one coming in with the reactants. True? So in some cases, it could go out hot, where it may came in cold. But in this special case, for this problem, the temperature in which it comes in, cold. The temperature at which it goes out, cold. So guess what? That's 0 and that's 0. True? All right. Is also the delta H for the CO2 because it goes out cold, 0. And the delta H for the carbon coming in and the delta H for the O2 coming in. All those delta H's, because it goes in at 25 and out at 25, it's all 0. True? Now, what about the enthalpy of formation? Well, you go back to the table. Can you remember what it was for the nitrogen? It was 0. Can you remember the enthalpy of formation for the oxygen? 0. Now we look. The enthalpy of formation for the carbon, that's also 0. In the table, it'll show you the first entry had 0. Solid carbon. So even though this coefficient was 3.76, it multiplied 0, so it didn't matter. Even though this coefficient on the O2 is 1, even though this one is 3.76, and this one is 1, and this one is 1, really our non-zero is the enthalpy of formation for the CO2. So we go look at the enthalpy of formation for the carbon dioxide, negative 393,520 kilojoules per kilogram, not kilogram, per kilomole. And guess what? That is a comma there, so it's 393,520. This was 0. Why was that 0? Because there's no work out of the furnace. And so our answer is that the heat transfer per kilomole of the fuel is negative that number. It's negative 393,000. What does the negative sign indicate? That it's not into the control volume, but it's out. It's exothermic, not endothermic. There's heat release. Well, if you solve the problem a couple times, you start with the energy balance equation, and you notice these enthalpies of formation are always there. And so what they did was they split out the enthalpy of formation and grouped them together into a new term with a new name. It's called the standard enthalpy of combustion. So the notation, it's on a molar basis. It's standard conditions going from reactants to products for that entity. Okay? All right. And so it depends on the stoichiometric coefficients and enthalpy of formation. Then that leaves only the difference between the standard condition and the exiting condition for all the products, and the change in the enthalpy between the standard condition and the incoming condition for all the reactants. All right. Maybe this is a little easier form, because what you could do is you say, well, if all of the reactants come in at standard 25 degrees C, this whole term is 0. And if all of the products go out at standard 25 degrees C, isn't that 0? And if it's a furnace, that's 0. So what is the standard enthalpy of combustion? It's how much heat would be released or transferred per amount of fuel. It's what we just calculated, true, for that carbon. All right. This brings up then the next important topic, heating values. This was the last two columns in that table A25. Notice that the heating values, they have two sides. They have a higher and a lower heating value, and they use the HHV for higher heating value and LHV for lower heating value. Pretty straightforward, true? Notice what units there are for the heating values. Kilojoules per kilogram. It's on a mass basis, okay? This is how much heat is released per kilogram, and they're the same for carbon. But for hydrogen, they're different. Why do we have two values? Go look at the reactor again. And what came out of that reactor? In general, when you have a hydrocarbon fuel and you have an oxygen source, let's say it's air, what comes out? Carbon dioxide. What goes out? H2O. What goes out? Nitrogen. Okay? They're going to have it for 100% theoretical air. If this CO2 goes out at this temperature and that pressure, do you think it could be solid, liquid, gas, or all three, or only one of those? CO2 at that temperature and pressure? There's no way you're going to have solid or liquid. It's going to be gas. Okay, same with nitrogen. It's only going to be gas. But what about water? Could I have liquid water at 25 degrees C? You can have liquid water at 25 degrees C. How does the water go out? Does it go out in the gas form, or does it go out in the liquid form? If it goes out in the liquid form, then it's going out at a lower enthalpy. If it goes out in a gas form, it's going out at a higher enthalpy. So you generated the water by combusting with a hydrocarbon. How does the water go out? If it goes out in the liquid, you get what they call a higher heating value. If it goes out vapor, then you get a lower heating value. So if you go back to this problem right here, how do I jump between the heat release for burning the carbon, solid carbon, and the lower heating value, which is the same as a higher heating value because there's no water vapor going out when you combust the carbon, right? How do I go from this number right here to that answer right there, which is right there? How do I do that? Well, the lower heating value is going to be the negative of the Q dot CV divided by N dot fuel divided by the molar mass of the fuel. So I move from a molar basis to a mass basis, that's all. So you take this number and you divide by the molar mass of carbon, 12.01, and you get that answer. You say to yourself, Professor, look at that number is not precisely the same as that number. You're right. Does it agree to 3 significant digits? Does it agree to 4 significant digits? Does it agree to 5 significant digits? No, but it agrees to 4. Professor, it seems pretty abstract that you could have a furnace and the water's not going to go out in the vapor state. For many years, you had a furnace. They would bring in some fuel oil, or even natural gas. They would burn it. And they would keep it separated by having a barrier between that and the air that goes through the furnace. And so it ingests it with a blower, and it throws out air, and then it puts it into your house to keep you warm. It also then, the burning of the natural gas is taken out with a flue, and it goes out the stack, goes out through the roof. You have a pipe that goes up through the roof. What they found is this goes out pretty hot. And what they'd like to do is they'd like to have more of the energy that's in the fuel go into heating your home and less of it go into hot exhaust products leaving your house through the flue. It doesn't take much to think of an annual fuel utilization efficiency given by this acronym. been out for a long time. And it's simply the ratio of how much energy is released during the combustion and how much of that energy then gets into heating your home, which is, if you subtract off how much goes out the flue, that's how much goes into heating your home, right? They rate furnaces that burn oil or natural gas, some fuel like that, based on annual fuel utilization efficiency. And over the years, they've even said to have a furnace where you really need the furnace up in here, you really need to have a higher percent annual fuel utilization efficiency. And for you guys down here, well, we're going to worry about the SEER number for your air conditioner. Remember? The SEER had to be higher in the southern climates. But the annual fuel utilization efficiency can be lower for the furnaces that sell down there. So this is now part of the changing landscape of appliances. Okay? So how do you get a high efficiency furnace? How do you get one that has this above 90% annual fuel utilization efficiency? Is you can't let the vent exhaust gases go out hot. And so if they can keep those below around 200 degrees F, then it's good. Okay? Well, what can happen is if you're burning some hydrocarbon fuel, that temperature can be below the dew point temperature of your exhaust. So what are you going to get? You're going to get a condensing furnace. That makes no sense when you hear it. You know, think about it. A condensing furnace. Like, make up your mind. What are we talking about? But it's a furnace where you'll have a burner right here. Let me try and show it to you. They'll bring in some air for combustion. They'll pass it through a heat exchanger, the primary heat exchanger, which transfers the heat from the hot gases to the indoor air that flows over it, and then usually goes up like that, and it's supplied to the interior of the house. There's a blower motor and a cold air return that is ingested. It's typically filtered right here or right there. So you're going to have an air filter. But down here, after the exhaust gases have passed quite a bit, there's a special secondary heat exchanger because you can start to collect condensate. It's now cooled off the combustion product so low. And that's what you want. You want to get all of that heat out of it, transfer it to the air that's going to keep the inside of your house warm in the winter. Now, what they have to do with these high-efficiency furnaces, they have to have a special fan. It used to be you could just let the flue be buoyancy-driven. And in probably the furnaces you own, there's no fan to push out the exhaust products. It's probably warm enough it just goes out because it's a low AFUE. But here, when you have a high-efficiency furnace, they have to have a fan, and then it'll blow it out. And usually you can blow it out horizontal. So if you go to modern homes up north, it's like you don't have to put a hole in the roof. You could just put it out the side of the basement, up near the wall, top of it. But you have to have some mechanism to collect up the condensate. And what do? You typically dump it off to a drain in the basement. And the drain could sit in there and then evaporate, or it could have a sump pump and throw it out after a while. Take a look at this problem. We have gaseous methanol at 25 C and 1 atm. It enters a furnace operating at steady state and burns completely with 100% theoretical air, entering in a separate airstream. The products exit at 25 C, so it comes in at 25, leaves at 25. Its kinetic and potential energy effects are negligible. Determine the heat transfer to the furnace from the surroundings in units of kilojoules per kilomole of fuel. Well, first of all, let's get a balanced reaction equation. CH3OH, 1 fuel, plus how much oxygen and nitrogen coming with the air goes to carbon dioxide. Right away, let's balance the CO2. What is in front of the CO2? Can you see that? 1. Then we'll move on to balancing the water. What's the coefficient in front of the water? So the coefficient in front of the water is 2. So now let's balance the air. What coefficient goes out here? When in doubt, go slow. So we get 2 oxygen from here. We got 2 oxygen. I can add that in my head. That's 4. But I already have 1 oxygen from the fuel. So I need only 3 from here. 3 over 2. All right. So now we finish out with a 3 over 2 on the nitrogen. Let's go to our energy balance equation. Q dot divided by N dot of the fuel. I'm going to leave off the work. It's 0. H bar enthalpy of combustion plus the sum of the N delta H bars for each of the products exiting minus sum of the stoichiometric coefficient delta H bar incoming reactants. True? But all the reactants come in at 25C. All the products go out at 25C. So all I have to do is calculate this enthalpy of combustion. This is just going to be the stoichiometric coefficient of the carbon dioxide times the enthalpy of formation of the carbon dioxide plus the stoichiometric coefficient enthalpy of formation of the water, H2O. And then I'm going to put it right here just to try and finish it out. This is nitrogen minus the NH bar not F CH3OH minus NH bar not F of the O2 minus NH bar F naught of the N2. Remember, this N2 is the reactant, that N2 is the product. All right. What about the enthalpy of formation of some of these terms are 0? How about for carbon dioxide? Is that 0? No. Negative 393,520. What about the coefficient in front of the carbon dioxide? 1. How about for the water? Enthalpy of formation for this water. This is where you have to say, is the water leaving in the vapor state or the liquid state? If we go to our table, right here, where is water in the table? Right here, isn't it? And you have 2 values, two rows, so the enthalpy of formation could be negative 241,820 or the other value. So we have to come back. So you'll get 2 times negative 241,820. How about the enthalpy of formation for the nitrogen? That's 0, thankfully. How about for the fuel? We had 1 mole of the fuel. It was methanol, and it was gaseous methanol. So it was negative 200,890 right here. And then we had the enthalpy formation of the oxygen and the nitrogen are both 0. So at this point, you do that math and you'll get the answer. It's a negative sign right there, sorry. That the heat transfer to the furnace from the surroundings is negative 676,270 kilojoules per kilomole. Now the next question is what is the lower heating value? Well, that's with the water going out in the vapor state, true. So that's good. Water vapor is going out in the vapor state. The lower heating value will be the Q dot divided by N dot F, make it a positive number, and divide by the molar mass of the fuel. The molar mass of the fuel is 32. And when you do that, you'll find that it is in great agreement with this number that is in our table. 21,110 kilojoules per kilogram. All right, I think we'll go ahead and stop there. Thank you for your attention.